Good morning. My name is Devrim Güçlü from İztek, and I will be chairing this first session of the day. And our first speaker is Professor Nergis Mavalvala from MIT.
Thank you. So hi everybody, welcome. Everyone can hear me? All right, good. So you guys have the terrible misfortune that you have to listen to me twice today. So I thought I would break my talks up into two parts. So the morning talk is a teaser. It's basically a very general level talk about the discovery of gravitational waves, how we did it, what we've learned so far. And then in the afternoon, I'll sort of give a slightly more technical look at where the field is going next. Okay, so this morning you can just sort of, everyone's just waking up, just hang out and enjoy. So I'm going to tell you the story of the 100 years it took to discover gravitational waves from the time they were predicted by Einstein. Before I do that, I do have to say that the discovery and the data and the instruments that I showed you is the work of over 1,000 scientists. So I'm just the messenger, but really I speak for both the LIGO and Virgo collaborations. Okay? So on February 12, 2016, so just a little over a year ago, every newspaper across the planet in pretty much any language you chose had a scientific discovery as a headline. And so what I want to do here today is I want to unpack that. I want to go past the headlines. I want to be able to tell you what exactly was the, what's the big deal, really. Okay, so it turns out that even though this was a scientific discovery, it also made its way into sort of the mainstream culture. So this is an advertisement that I took a picture of in the New York City subway. And it says that scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a big closet. So now I happen not to agree with this, but I don't think it was easier, but I was very tickled by the fact that this is now even, appearing in the subway as an advertising tool. So what's the deal? All right, so before we talk about gravitational waves, I want to just step back and tell you what we know about the universe from light. Now, I obviously can't tell you everything, but I want to give you some sense of how light has been our friend over the millennia. So here is one of my most favorite pictures in astronomy. And what this is this is known as Cassiopeia A, and it's a supernova remnant. So what we know about this object is that it was a star, like kind of more or less like our own sun, a little bit heavier. And as with most stars, at the end of their lifetime, they run out of nuclear fuel that keeps them shining. And as a result, their light source turns off. And when the light source turns off, the star's gravity causes it to implode because there's no more radiation pressure pushing outwards against that gravity, and the star goes supernova. So that's what this picture is of, but it is actually more interesting than just that. This is a star just about 10,000 light years away that went supernova about 300 years ago. But what's more interesting about this picture is that it's actually taken with 3 major telescopes. And these are all 3 space telescopes, different wavelengths. So the reddish colored stuff is infrared light taken by the Spitzer Space Observatory. The yellows and greens are optical or visible light, and that's taken with the Hubble Space Telescope. And then finally, the blues and purples at the very edges are X-ray emissions taken by the Chandra X-ray Observatory. And one of the things that you notice right away is that the different colors of light tell us about the energetics of the system, right? The most energetic, hottest stuff is blown out the farthest, for example. Now, there's another thing that's really, really neat about this picture. If you look in the very, very center, do you see a tiny little blue dot? I'll point it to you right there. So that is a neutron star, visible only with the X-rays. It's only blue. It doesn't show up in the other colors. And that is the remnant star that was formed when this star collapsed. So what's the properties of the neutron star? The property of the neutron star is that it weighs about the mass of our sun, but it has a radius of just 10 kilometers. So it's an extremely compact, dense object. And if this parent star that went supernova had instead been more massive, if it had been more than 3 times the mass of our sun, in fact, this neutron star would have continued to collapse into a black hole. So from here on, you can just think of neutron stars as cousins, as the lighter cousins of black holes. They formed in the same processes, it just depends on the mass of the parent star. Now, if indeed this were a black hole, we would not have been able to see this image. And in fact, what we've known about black holes until the LIGO discoveries has been inferred through black holes accreting matter. Okay? So here is an artist's rendition of a black hole. And the way that these black holes have been observed, for example, in the X-ray, is essentially by the fact that these black holes are accreting matter from a companion. So material is falling in because of the extreme gravitational conditions that material is heating up, and that usually emits in X-rays. And so we see these just as X-ray emitters from this falling in stuff. But this requires, a system like this requires that this black hole be paired up with ordinary matter. So some kind of ordinary star or gas and dust to be able to see it. If it were sitting on its own in space or in a binary with another black hole, you couldn't observe it this way. And that then brings us to the question of how might you observe it. And immediately, as soon as you think of a black hole, we've all learned that black holes are objects whose mass is packed into a small enough volume that this escape velocity is the speed of light. So small mass in a small volume means strong gravity, and gravity becomes our friend. So let's look a little bit at what we know about gravity over the last several hundred years. So our first hero of gravity was Newton. And Newton had this incredibly successful theory of gravitation. It's called the universal law of gravitation. Today we know it's not so universal, but at the time it was even called something so magnificent. And it's a very simple theory. We are all physicists here. We all learned Newton's law of gravitation, one of the very first pieces of physics most people learn. And it tells us simply that if you have two masses, M1 and M2, they feel a force of attraction that's proportional to their masses and inversely proportional to the square of the distance between them. Now, Newton himself worried about something called action at a distance. And it turns out long before him, even Aristotle had worried about this. And the question that they worried about is, how does mass 1 know about mass 2? I mean, it was understood already that these masses were separated by astronomical distances. How do they influence each other? And that puzzle didn't actually get solved till our next hero of gravity entered the picture, and that was Einstein. And so, 300 and some years later. And Einstein actually said, forget about gravity as a force. Gravity is not a force. Gravity is the warpage of space-time. And Einstein also wrote a formula, a very sweet-looking formula right here. Look how simply it sort of looks like this formula on the left, and it describes the geometry of space due to the presence of masses. And I'll just say right here, this is one of the most beastly, awful equations ever written. It's taken 100 years to get exact solutions of it. Those are done numerically. And so even though it's a very innocuous-looking formula, it contains an enormous amount of information, but also very hard to solve. So Einstein's picture, we all know, gravity is space-time warpage. You put a massive object in some part of space, and it will curve that space-time. Now, Einstein, out of his field equations, he also came another thing. He asked the question, what happens if you take a massive object and you don't just let it sit in space? What if you allow it to accelerate? And then what he found out of the field equations was that the entire space-time itself would ripple. And in fact, so here's a static object that deforms just space around it. But if you have accelerating objects like this pair of neutron stars or black holes, it could be ordinary stars too, just that those are very weak emitters, the whole space-time will ripple, and these ripples propagate out of the source at the speed of light. That's what Einstein found from his field equations. They actually popped out. Now, I will just say, because I promised you I was going to tell a story, I have to tell the story of Einstein and gravitational waves, which is that it was not at all a happy friendship. Einstein remained very, very ambivalent about gravitational waves, more or less throughout his career. So it starts in 1915, where he wrote the first rendition of the general theory of relativity. He actually gets the gravitational wave part correct in a later paper in 1918. The first version wasn't quite right. Now, in 1918, Schwarzschild also proposes these stars that have so much mass that light cannot escape their gravitational pull. Einstein actually did not like these dark stars at all. They were known as dark stars. Today we know them as black holes. At the time they were known as dark stars. And he actually really thought of them as some mathematical anomaly of the field equations. He did not think nature could do such a thing. Now, it turns out that he vacillated several times in his career about gravitational waves, and the most important and documented one of those is in 1936. So, long time, so sort of 20 years later, he actually wrote a paper with Rosen, and in which he retracted the existence of gravitational waves. So this is Rosen, the same Rosen of EPR, Einstein-Podolsky-Rosen. And what the title of the paper was, "Do Gravitational Waves Exist?" ? And as soon as you get through the very first few lines of the abstract, the answer is no. So this paper was sent to Physical Review, 1936, and it was, for the first time, it was sent out for peer review. And the peer review was done by Robertson, who is another sort of big name in cosmology and relativity, Robertson of the Robertson-Walker metric, for those of you who are familiar with that. Robertson sent back saying this is not correct. So the editors of PRL sent back to Einstein saying, sorry, but here are the problems with the paper. Einstein wrote back saying, I sent you this paper for publication, not for review. And he never again published in PhysRev. Okay? In the meantime, the paper itself got published in an obscure journal of the Franklin Institute. And then in discussions with Robertson and Infeld, Einstein eventually retracted the retraction. So you can see that he kind of went back and forth a few times. But really, I have to say I'm an experimentalist. And I have to say that in the end, none of this matters. The doubts and controversies kind of subsided after a very famous conference at Chapel Hill in 1957 with the work of Feynman and others. But as an experimentalist, I can say none of this matters. In the end, observation and experiment always have the final say on any theory. So my apologies to the theoretical folks in the room, but if your theories aren't what nature does, then it doesn't matter. So now this is going to be what we are going to look at. So what was the observations that followed? Well, so it turns out that in 1934, Body and Zwicky proposed neutron stars. So this was a theoretical proposal. It should be possible to assemble stars made up entirely of neutrons, and neutron degeneracy pressure is what's holding them up. In 1967, Pacini and Gold proposed that these neutron stars could be spinning rapidly about their own axes, and those today we know are pulsars. And indeed, in 1967, the same year, the first pulsars were observed using radio telescopes. Now, pulsars are nice because they have very strongly beamed emissions, so they are nature's lighthouses, and those were observed by looking at the lighthouse pulses in the radio. So first observation of pulsars came in 1967. Now, it turns out, in the same time, this man, Joe Weber, announces in 1969 the discovery of gravitational waves. And this kind of set the physics world on fire, because it was recognized after people saw the first pulsars that it should be possible to have strong enough gravitational waves that they should be observable. Weber announces that he saw them with this device. Basically, the device is a big chunk of metal, and his idea was that as a gravitational wave passes through it, it'll get it ringing, just like if you tap a wine glass and the wine glass rings. And then he instrumented it with these sensors so you can pick up that ringing motion. Many groups immediately jumped in and started to reproduce these experiments. No one could reproduce the results, and eventually it became known that this was an incorrect or false claim. So that was the first sort of rocky start to the attempts to detect gravitational waves. In 1971, the first black hole was discovered, and then the sort of the linchpin of this whole business with gravitational waves detection at that time came with the discovery of a double pulsar system in 1974. So what happens there is you have a pulsar, that's a nice nature's lighthouse, and normally the pulsar is spinning about its axis and you measure its pulses. Now this particular pulsar was in a binary with another pulsar. So for the first time we have a strongly gravitating system, and what Hulse and Taylor measured was that the timing of those light pulses changed because of the orbit of this pulsar with its companion. And in fact, they measured that that orbit gets smaller in time because as the system radiates away gravitational waves, that energy comes out of the orbit, so the orbit has to shrink. And then, so this was their data from 1975 to 2005, and on the vertical axis is simply just the size of the orbit. The data points were what they measured, and the solid line is the exact prediction from the Einstein equations for what the system, what the system should do. So this was considered the final sort of nail in the coffin that gravitational waves really do exist. And in fact, this also impressed Sweden, and they got the Nobel Prize for this measurement in 1993. Now, I just want to go back and tell you, Einstein's ambivalence was completely justified. So he died in 1955. And so neutron stars or black holes were not discovered by then. Certainly, if you, as he did in his original 1915 paper, if you make the numbers for how much gravitational radiation you would get from an ordinary star system, it's laughably small. And he, in fact, wrote in that original paper, if you translate from German, pretty much along the lines of these will have no practical value. So he recognized that they were immeasurable and impractical. Even so, I have to tell you something remarkable about those equations that I already have dissed so much about being so difficult. Encoded in them was really very, very accurate predictions for gravity, space-time, and black holes. So let me show you a movie, and this is a movie that actually is made using numerical solutions to the Einstein equations. And it really is also truly 100 years in the making, because these solutions using numerical methods have only sort of become available since about 2005. So until then, people could not get even simple systems like a pair of spinning black holes to actually orbit each other and eventually close the orbit and collide. So what you're going to see in this movie is a few things. On the bottom here is actually the signal that's going to accumulate. This is the actual ripples in space-time or the gravitational wave strain. And on the vertical axis here I'm sorry, not the vertical. On this movie here, you see two black holes. Let me start playing it. The color coding tells you the curvature of space-time. It's a two-dimensional cut. The actual topology will tell you the space-time curvature. The color tells you about the flow of time. And finally, the arrows you can ignore. It tells you about frame dragging, which is kind of a detail. But what you see is these two black holes are orbiting each other. Initially, the space-time just below each one is warped, or in the vicinity of each one. As they get closer, their space-time warpage starts to interact and gets larger. And eventually, the movie will actually stop when the horizons touch, and you'll see at that time, at that moment, the space-time is incredibly warped. And in fact, this is the part of the simulation that people couldn't do very well without the numerical method. So very warped. And then you form a single black hole. You had the peak signal as they touch, and the single black hole, its normal modes bring down, and the signal shuts off. Gravitational waves then propagate off into the universe. So one of the things that I really, really find amazing about this movie is that it's the first time that we've had to be, we've been able to have close enough exact solutions. Okay? Now, also in the 1960s was a very important time for this whole business. So also in the 1960s, this man, Kip Thorne, neutron stars and binary neutron stars had just been discovered. He was one of the first people to put a number on what would the strength of gravitational waves be. So this is the waveform that was predicted from those Einstein equations. And on the vertical axis is the strength, and that turns out to be an amplitude of 10 to the minus 21. And that's for a pair of neutron stars in a galaxy not too far from our own. Okay? So he comes up with this set of numbers. and it's very depressing. It's a small number, but even for these highly gravitating systems. So you can then ask what are the possible sources of gravitational waves? And what you see right away is that there's a nice rule of thumb scaling that you can carry. L here is the luminosity of gravitational waves, so it's the energy density, if you will. It scales as the size of the object r compared to the Schwarzschild radius, which is simply just the size of a black hole of similar mass, okay? And that goes as the square of that quantity. And it also scales as the velocity of material in the object compared to the speed of light, and that goes as the 6th power. So you need only 2 ingredients for this to make a good source. You need the sources to be compact, so you need the radius to be comparable to the Schwarzschild radius, and you need them to be relativistic. And that immediately tells you you cannot conceive of any sources made here on the Earth. You can't do experiments like people love to think about with spinning dumbbells, etc. The radiation is just too weak. It also tells you that you need neutron stars and black holes. You can't make enough of this with ordinary stars. And you need rapid accelerations, which means you have to have orbits, explosions, collisions. So it's got to be both warped and violent. Okay? Now, what that means is that your prime candidates are neutron star and black hole binaries. Supernovae. That's considered a source that could be pretty viable, with one sort of caveat, which is that when stars explode and they go supernova, people don't really know very well how spherical the distribution of matter is. If the distribution of matter of the ejecta is very spherical, the radiation is very small because its lowest moment is quadrupolar. So there's a big unknown there, but they're there. The Big Bang itself turns out to be one of the most amazing sources of gravitational waves. And the reason why is that gravitational waves might be our only way to look far enough back in time. So we all know that what we know about the Big Bang and cosmology comes primarily from observing the cosmic microwave background, which is infrared light. Now, it turns out that the universe was too hot and dense for light to escape until it was about 400,000 years old. So when we look at the cosmic microwave background, it's basically the universe when it was 400,000 years old. If you want to look further back in time, light can't do it because the universe was opaque to light at the time. But it was completely transparent to gravitational waves and to neutrinos. So if you want to look at what was going on in the universe before the time that light was decoupled, you have to use one of those tools. And so gravitational waves are, believe it or not, easier than neutrinos for that kind of measurement. Even so, I'll say with the instruments that I'll describe today, that's not likely to be something that those instruments will be capable of seeing in this generation or at least the next. Okay, and then there's, of course, always unknown things that we haven't thought about. So that's the kind of sources we should expect. So real quick recap. They're predicted by Einstein's theory of relativity. They're ripples of space-time itself. And now comes a very important question that was asked during that 1957 conference. Until then, what people got stuck on was what does a source of gravitational waves do? And that was a solution people weren't finding. And at that conference, was asked the question, what do they look like at a detector? And so here's the answer. At the detector, they basically cause changes in space-time distances. So if you have a space-time distance L, and a gravitational wave of amplitude h comes through, that changes by an amount delta L. And so that was the key piece of its properties that we'll use to design detectors. This is a nice little simulation that shows this as a strain. What you'll see is this is a grid of points, and if it's a true strain, then as the gravitational wave comes through, the distance between the points will change, but the points that are the farthest apart will also have the greatest changes in separation. So, it doesn't play, but if it did do it. So the scaling now is clear. If we believe Thorne's initial numbers of 10 to the minus 21, then if you had a detector of scale 1 meter, which is a reasonable number for most labs, you would have to measure changes of length of that detector at the level of 10 to the minus 21 meters, which is a horrendously small number. When I put up strain of 10 to the minus 21, you might not be so concerned because it's kind of dimensionless, but as soon as I put a dimension on what the challenge of the measurement is, it's really god awful. Okay. Even so, one can ask how one might detect these. And the idea of these detectors is very simple. It's as simple as this. You have a laser, you reflect that laser beam off a mirror, the light comes back to you, you have a clock, you measure how long it took the light to travel that distance, whatever distance you put between your laser and your mirror. Now, it turns out that as a gravitational wave comes through, that distance would change and the time of travel of the light would change. So that's very simple. It turns out that there are not clocks good enough to do this measurement by orders of magnitude. And so you're then forced to make a slightly more complex measurement, which is an interferometer, where you simply do the same thing, but you use a laser beam that's split in two. And the reason why this works better than just the simple linear version is that one arm of the interferometer can act as a reference for the other. And as a result, you don't need an absolutely precise clock. And so that's really the only reason that these detectors are L-shaped interferometers and not just linear devices, okay? Now, once you do that, you have two things you have to do. You have to make mirrors that are very, very still. That means you have to have a lot of vibration, isolation, and thermal control. And once you make the mirrors very still, you need to be able to measure that tiny motion, and that's where the laser light comes in. The laser light is our meter stick, and that means we also need very ultra-precise optical measurements. So those are the two things you have to do. You have to do them very, very, very well, but that's about it, okay? All right, so this idea was put forward by Ray Weiss, so also in the late 1960s at MIT, and the idea was to use an interferometer. And by the way, that idea had been around also independently in Russia to use an interferometer to make these measurements. The thing that Weiss did that was different and kind of, again, revolutionized our thinking about this was he understood that you could not make a measurement on a meter scale interferometer. That measuring changes of distance of 10 to the minus 21 meters was too hard. He said, let's make them long, make them kilometers long, and then you have to make displacement measurements of 10 to the minus 18 meters. And he said, well, that we can do. And this was in the late 1960s to early 70s. So Thorne and he then get together in the early 1970s and start to lobby and propose for an experiment to do this, a kilometer scale experiment to do this. And that's how LIGO was born, which is, these are the aerial views of two detectors, one in Louisiana in the United States and one in Washington, 4 kilometers long. And if we do everything right, they should be capable of measuring 10 to the minus 18 meters. Okay? So that's how this got started. Here's a little tour of the observatory. So here is the Louisiana detector, L-shaped as promised. The laser sits in the center here, and the laser beams travel 4 kilometers along each L. They come back, they actually interfere back here, and we make the measurement. Now, the laser beams themselves travel inside of this stainless steel tube that's at ultra-high vacuum. And the beam tubes are covered by this concrete shield. And at the time that LIGO was being built, there was a lot of discussion about whether it was worth the cost of this concrete shield, and it has turned out to be quite valuable. This is actually, it's not Photoshop, this is real. This patrol car came over this dune this is at the Washington Observatory, it's in the high desert, and they simply didn't notice that there was this 4-kilometer long barrier in the middle of the desert. So the car was damaged, no one was hurt, nor was our instrument. And so the barrier the concrete shield has been important. Inside the observatories, on the main experimental halls, you see objects like these. These are actually just the vacuum chambers in which each one of these holds a single mirror of the LIGO detectors. And they're pretty big. If I stand beside these, the top of my head will be just below this row of viewports. They need to be this big because each mirror itself is quite big. These are not ordinary lab mirrors. The mirrors themselves are about 35 centimeters in diameter, 40 kilograms in mass, but they're also sitting on tons and tons of vibration isolation apparatus. And that's what the vibration isolation apparatus looks like, some part of it. That's a spring mass system, just like the shock absorbers in our cars. The mirrors themselves, like I said, 35 centimeters in diameter, and those are hanging as pendulums. And the idea there is that when you hang something as a pendulum, that gives you isolation above the natural resonant frequency of the pendulum. And then finally, that is the laser. This laser can put out 200 watts of light at near infrared, and that's basically the meter stick that we use to make the measurement. Control room from where everything is controlled. Okay, so if you've never had a chance to go to one of these, this should give you a flavor of what it looks like. Now, I like to sort of just point out, I've been working on this for 25 years, and so I've also had some adventures. So here is a younger, narrower version of me looking at, this is at the Washington Observatory again, looking out at a tremendous desert fire. And this desert fire approached the observatory. This is, again, the edge of our roof. And then it turns out that the concrete barrier, the same one that kind of caught that patrol car by surprise, became the fire break for the fire not reaching the town that was to the east of the observatory. So observatories have had other uses, not just gravitational wave detection. This is at the Louisiana Observatory, and if you look at this little row of rods here, this row of rods was put in here to mark the trajectory of gunfire. And so during hunting season, someone took a shot at LIGO, and in fact, this cartoon then appeared in the local newspaper. It says it's hunting season, time to set the lasers in self-defense mode. So, you know, there's been lots of adventurous things that happen when you work at big experiments like this. And this is, again, just a picture in the control room. There's me in the far end. Now, in more recent years, I haven't been working directly at the observatories as much. What I've been working on is developing the technologies that go into the LIGO detectors, and I will talk about those things in the afternoon talk. Okay, so it's just a teaser. Now, fast forward, observatories have been built. And indeed, what we have is, in September 2015, was this LIGO detects for the first time what we eventually learned were binary black holes that collided. So here's, again, a nice movie of what that black hole system was actually doing. Pair of black holes collide, and gravitational waves radiate outwards, pretty much exactly as Einstein had instructed them to do. They propagate through the universe, and we learn from our data, and I'll tell you in a moment how, that they actually propagate for 1.3 billion years. And then eventually they find our beautiful little planet. And here's the signal. Arrived first at the Louisiana detector, and then 7 milliseconds later at the Washington detector. Now, this didn't really happen. This is a vastly exaggerated scale, I hope you know. But it basically gives the trajectory of the signals, and this is what we saw. And these pictures, by now, everybody's seen. This is a pretty iconic picture of that first detection, but I want to point out a few important things about it. The first thing to notice is the vertical scale, which is the strain or the amplitude of the wave. And you notice that at the peak, which is where the two black hole horizons just meet, the strain was 10 to the minus 21. So check mark for Kip Thorne. This is a prediction that dates back 45 years, and that was pretty amazing. Now, you also notice the other thing, which is that if you convert that signal into motion of the LIGO mirrors, that corresponds to a few times 10 to the minus 18 meters. Check mark for Weiss. This is something he also told us 45 years ago that could be done. So that's the first piece. The other thing that's really remarkable about this is look at the time scale. So the time scale is 200 milliseconds. And so what we're seeing is the last 200 milliseconds of this binary black hole system. The system probably was formed over 1 billion years ago. So it's really remarkable that this system is 1 billion years old, and we have seen the last 200 milliseconds of its life before it perished. Okay? Now, these signals have been seen everywhere, from newspapers to Scientific Americans. What do they mean? That's really the question. So here is a numerical relativity model of that signal. Early on, when the two black holes are far apart, you just see kind of a sinusoid. As they get closer together, they're orbiting each other faster, and the signal amplitude also grows. Where they touch, you get the maximum signal, and then when the single black hole forms, it turns off. Now, from this frequency evolution, the way that the frequency changes with time, you can get the masses of the black holes. Then, once you've done that, from the amplitude of the wave, you can get the distance to the source. And then finally, from this final ring down and decay, the frequency and decay time, you can tell the mass and spin of the final black hole. So all of these properties are encoded in this signal. And so when you put it all together, what we saw was a pair of black holes that, this is another beautiful movie because this is now putting the same black holes in a star field, and you can see all the general relativistic effects of of Einstein rings, that's light behind the black holes, etc. But really what it is we now know they were 1.3 billion light years away. We know that we got this last 200 milliseconds of their life before they collide. We also know that the new black hole, we know that they were 30 solar masses each. We know that the new black hole that formed was lighter than the two parents, which means that energy must have been given off in gravitational waves. And what we know is that it was about 3 times the mass of our sun. So now you can also put a real scale on this. Here you have 30 solar mass objects. At the moment that their horizon touched, they were going at half the speed of light. They were 1.3 billion light years away, and in that few hundred millisecond time span, they radiated 3 times the mass of our sun. So let me just say something. This is something I think about a lot. You know, if you wrote this down as science fiction, you could not have imagined nature really does this. Imagine something that's 30 times the mass of our sun going at half the speed of light. So it's really kind of remarkable event in nature. Now, it turns out that the 2 black holes, of course, did not live happily ever after. They perished. And what we got instead was this bigger black hole, which will probably, for this system, live quietly and lonely life for the rest of its life, because it's not in a star field, it's not near matter, we will never know about it again. It will just kind of float its life away. So it's a pretty lonely life for this new guy, unless later on I'll tell you maybe it'll meet a companion. All right, so LIGO's first observing run resulted in 2 other detections, one that was high enough SNR that we can call it a confirmed detection, and another one that was in October of the same year that had a 90% chance of being a black hole. So its signal-to-noise ratio wasn't high enough for us to say it's a full bona fide 5 sigma detection, but it's got a pretty good shot. So I like to say in that first observing run, we saw 2.9 events. Okay? So, and all of them turned out to be black holes. Then LIGO went through a period of shutdown for a year to make improvements to the detector, and then you might have heard just earlier this month that in the second observing run, we've seen another black hole system. And this one also has some interesting things that I'll talk about in a moment. So this is the black hole. By the way, all of these gravitational wave events are named by the date on which they were seen. So the year 2017, first month of January, the 4th day. And here again are the signals and the model that goes with them. The parameters of this newest source is 30 solar mass and 20 solar mass pair. And what we see again is that roughly about 2 solar masses was lost to gravitational waves. And the other thing that's very interesting to see is that this system is about twice as far away as the original first loud one. So it's a more distant black hole system. Okay, so what are we learning about black holes? So what we're learning are a number of things. So one of them is simply, look, before this moment when LIGO observed these binary black holes of stellar mass, we didn't know if they existed. We expected that they should, but never been seen before. We didn't know what mass range to expect. And in fact, if you look at what was known about stellar mass black holes from those X-ray studies that I showed you at the very beginning, where the black hole material falling onto the black hole glows in X-rays, these were the masses that we saw. All of them were sort of in the 10 and maximum 15 solar mass range, right down here. Now, LIGO has started observing a population that's really quite a bit heavier. The component masses can be as small as the X-ray binary ones, but we're also seeing much heavier black holes. And that puts up a big question about what the formation history. Where do they come from? How do we get, if we believe black holes are formed from collapsing stars, how do you get a star that's 30 times the mass of our sun? We know stars don't usually grow that big. So this provides new mysteries and new populations to study. What else have we learned? Well, from these signals, we can do tests of general relativity. And that asks the question, is general relativity the correct description of these black hole systems? And so you can actually make a measurement from the wave. You can measure the dispersion relation, which simply says that waves of different wavelengths should travel at different velocities. And by doing that, we've put some of the tightest constraints on the mass of the graviton, because in general relativity, the graviton, the waves are supposed to be dispersionless, which means the graviton should be a spin 2 particle, and so and massless. And so we can put a constraint on the mass, and that turns out to be just about 10 to the minus 22 eV for people who like to carry those numbers around. It's also a very powerful systems for constraining our understanding of general relativity in perturbation methods. And one of the most common methods used are post-Newtonian expansions, where you simply take GR and you write it in terms of V over C as Newtonian gravity with corrections. And those tests have also been done. Now, that's the test of general relativity. Now, what about on the astrophysics side? On the astrophysics side, for this newest detection, we went from 2.9 to 3.9 events. And for the first time, what we're able to do is we're able to start asking the question, how many black hole binary systems are out there? So we can constrain the rate at which they merge. And most interestingly, in this newest event, we also have some slight evidence, and I'll say slight because it's really in the sort of 2.5 sigma level, so you can't get too excited about it, even though you think I'm excited, that we have some evidence that the spins of these black holes are misaligned. And that's actually pretty important for starting to understand where do they come from. So let me just say a few words about that. So where do we think these stellar mass black holes come from? Well, there's two possibilities. The one is that they're born as twins. And what that means is that they're part of a binary star system. And when one star of the binary goes supernova and forms a neutron star or black hole, then the other star, it kind of envelops the other star, and they evolve together till the second star goes supernova, and now you get left with two compact binaries. Now, in those systems, you have mass transfer, and mass transfer tends to align spins. So the angular momentum from mass transfer tends to make the spins of these two black holes align with the orbit. The alternative is that they are actually born as singles, and then they live in a very dense star environment, and they capture another black hole. That's called dynamic capture, or they meet each other in these dense stellar environments. And in that case, there is no mechanism to expect that their spins should be aligned. They should be completely randomly oriented. And we're starting to see maybe that first little evidence that maybe we're seeing this latter scenario. Now, let me put a grain of salt on that. If you ask, what is the rate at which you should see binary black hole mergers from either mechanism, neither of them is enough to explain the rates we're seeing. So either both are at play, or there's even yet more mechanisms we haven't thought about. So we're just starting to understand how these black holes form and evolve. So what lies ahead? This is just the teaser for the afternoon now. One of the things that we know is that gravitational wave detectors are not very good at localizing the object in the sky. If you make these observations and you ask where in the sky was it, the best you can do for these observed systems are sort of 1,000 square degree patches. If you want to then follow those up with a telescope, that's laughable, because telescopes have sub-degree resolution, and so it would take you days and days to map out such a big patch of sky looking for some electromagnetic counterpart. Now, if you had more detectors, and for example, if you had a detector in Europe, and it turns out we do, we have the Virgo detector. If the Virgo detector had been on the air when these detections were made, the localization would get quite a bit better. And especially for that very first, very loud event, it happens to be very well oriented for being localized well. So that gives us a lot of reason to say we want to have more detectors widely spaced available. And that sort of indeed is what's happening. There's the global network of detectors. The two LIGO ones in the US, a 3-kilometer long detector called Virgo in Europe, a 3-kilometer long detector in Japan, Kagra, which is under construction, and then a planned 4-kilometer LIGO detector in India. And And also, of course, the Space Observatory, LISA, which I'll say a word or two about in a moment. So if you then had, this is the coverage of how well you could localize a pair of neutron stars on the sky. You can see in some parts of the sky, just with LIGO and Virgo, you can do pretty well. Other places you do pretty badly. And in fact, the red crosses are places where you have no sensitivity at all. If you then add, say, the India detector to this network, then you can start to constrain it like this. So if you haven't followed, smaller patches is better. And so that's the motivation for this global network. So I'm going to finish my talk just by saying, what all the excitement was about. So these were the first direct observations of gravitational waves. We have not seen this ripple of space-time in any other measurement before. There's also now we're finally starting to see binary black holes, and really for the first time. We've never really known if they were there. We thought they should be there. So also, the first times we're able to test Einstein's theory of general relativity. And this is actually not something that just is a little theoretical exercise or for theoretical pleasure. There's really important things to happen here. So remember our old friend Newton? So Newton had this very successful theory, but already well known before Einstein was that Newton's theory explained planets, moons, but it did not explain correctly the orbit of Mercury. Now, what's special about Mercury? Anyone? It's the closest to the sun. So Newton's gravity already started to break down when you got too close to our own little pretty sun. And as a result, it's very important to ask, is Einstein's the correct theory around these highly gravitating systems like black holes? And we know now that black holes are a really important building block or ingredient in the early universe to assemble the universe we have, so we better get that right. And then I'll say for myself, as a personal thing, having worked on these instruments for 25 years, I'm really happy that the damn instrument works too. Okay, so that's been a real pleasure too. So indeed, we've turned on a completely new way to look at the universe, but I think even more importantly, it's that we have actually started to use gravity instead of light, and that kind of is a new tool. So really, this list of things that I put in white, those are the things we're really happy and proud about right now. But when our generation is remembered for the science of this, we'll not be remembered for those early discoveries. We'll be remembered for the paradigm shift. And very much in the same way as Galileo is remembered we believe, actually I'd love to ask the friends in Turkey about this, because you have a better sense of this than I do. We believe that Galileo was the first person to point a telescope at the sky. Now, with many such statements, I usually find that was done earlier somewhere in the Eastern world. So if anybody knows of a telescope that came before Galileo's in 1609, I'd love to know. But imagine that it is Galileo. No one really remembers what Galileo saw through his little telescope. What's remembered is the paradigm shift, that for the first time humans use an instrument instead of the naked eye to look at the sky. And since then, we've done amazing things with telescopes. We've made them bigger, we've made them in space, we've made them of colors that our eyes couldn't even see. And that's where we are with gravitational waves. The gravitational wave sky is just like the light. The wavelength of gravitational wave spans 20 orders of magnitude. And what we've done now is with these Earth-based detectors, we've just started to see the fastest gravitational waves that we can. And I'll say in my afternoon talk why we can't go to longer wavelengths. But the space detector will be able to do these slower or longer wavelength waves. And then there's a number of other tools for going farther back. So I just want to leave you with this thought that this is just the beginning. I told you it was a story, and I've told you the 100 years it took to get here. But I can't tell you what the next 100 years will be, but it's going to be interesting no matter what. So thank you.
Thank you very much. Do we have any questions? Yes.
How important the wavelength of the laser? I mean, you said near infrared or something, so can you use some visible?
Yeah, so the question is, how important is the wavelength of the laser? So look, really the laser wavelength is determined by technology, not by something fundamental. And what is the technical requirement of the laser? I told you that the laser wavelength or the stability of the laser is really important because the laser wavelength is basically our ruler. So you can think of it just this way. You can think of it as, imagine I give you a piece of paper and I give you a ruler, and I say measure this piece of paper. But the ruler I've given you is kind of crappy. And what it does is the tick marks on the ruler tend to fluctuate. So you try to measure your piece of paper and you get very different measurements each time. And that's what lasers are. Laser wavelengths are not always very stable. So the choice is made for getting the most stable lasers that can still put out hundreds of watts. So that's the choice. And that turns out to be, at the time that LIGO was being designed, these 1064 nanometer solid-state lasers. For future detectors, and which I'll talk about in the afternoon, that question is on the table again, because laser technology has also evolved in the last 20 years tremendously. But for these, that was the choice.
Maybe, okay.
So when you look at the data with two detectors, I mean, it's tremendously overlapping, but there is quite difference, small difference. And could you comment on that?
Yeah, so absolutely. So the question is, when you look at the data, especially if you look at the time series, you see that the two signals are not exactly the same. And they aren't in part because the detectors aren't exactly identical. They have slightly different frequency response, and they have slightly different background noise. And that's, of course, taken into account when we reconstruct the model and reconstruct the signal-to-noise ratio. But the differences in the detector are what gives rise to the differences in the waveforms. And so the model waveforms that are used are the ones that are the highest likelihood for a joint, or coherent detection. So.
Is it possible to have a compact interferometer where the light travels back and forth, between mirrors, for example?
Yes, it is completely possible, but that's already done. So I'll talk about that in my afternoon talk. But LIGO is not just a simple Michelson interferometer. Laser light doesn't just leave the beam splitter, go to the end, and come back. It already has fibrillar cavity, so the light is already being bouncing 200 times. And that's about the most you can do when you want to have mirrors of that scale in terms of the losses in the cavities, before which you can't maintain the light in there. So it's already close to optimized for that. So you had a good thought, and that thought was had by people in the 1977 or so. So it's been around since then.
Yeah, time for more questions.
You mentioned that the observation of such big black holes with 30, 40 sun masses is a little bit of a mystery because you don't know how they're formed. Why can't we think of a dense cluster with little black holes merging eventually forming these?
So that's certainly one of the possibilities that's formed. Now, it turns out that it's this dynamical capture process is not as easy as it sounds. It's because, first of all, it's not a two-body process. If you just take two black holes and they come into within gravitational binding distance of each other, they actually just change trajectory and keep going. So right away you need a third three-body interaction to do that. And then if you ask the question of what are the density of dense stellar clusters, and what is the formation rate for that, it's too low. So that's the one thing. So you can certainly think of this is called a hierarchical, building up. So you get little ones and they keep merging, but they don't merge fast enough for us to see these. So then the other thing you can say is, well, then they must be born from heavy stars. Well, it turns out that in the very early universe, among the first stars, they were heavy. And that was because they were, at the time, very metal poor. Metals hadn't yet evolved. And by the way, if you don't know, for astronomers, anything heavier than helium is called a metal. But so they were, they didn't have heavier elements. And it's the heavier elements that actually constrain the size of stars. So as soon as heavy elements started being formed, stars couldn't grow to 30 solar masses. In fact, the few examples we know of are called population 3 stars, which are the oldest stars in the universe, and those are typically out at redshifts of 10, 20. So it's really quite mysterious at the moment, but in a good way, right? I mean, this is the beauty of discovery, is that right away it opens up new questions. So, job security for generations, right? So,
Thank you.
yeah.
The event rate was a big mystery before you turned out a machine. Now you said there's roughly the idea of having 13 events per year on the lower end. So can we expect monthly detections from now on? Does that mean that?
Yeah, so I would say on average it means that. I would say at the moment with the sensitivity of the detectors, I think the number is closer to like 1 every 2 or so months. Roughly speaking, that's true, but you know that that's not exactly how Poisson statistics work for small numbers. So, but I think if you integrate over some, many months of observation, that was where it came out. If you ask how much observation has LIGO already had, it's actually much shorter than it looks, because even though the first observing run was 3 months long, the actual time when both detectors are up and running in high sensitivity mode is probably about 2/3 of that. And then with the second observing run, it's been even a little bit worse. So I would say, if you say the duty factor is 50%, we've been running for 6 months, we've about 3 months of observation time so far. So I think it's closer to 4 by now, but that's about the number. But the thing that's very interesting is if you look at the constraints for the rate, it's still very broad. The rate that we think these binaries happen at is between 10 and 200 per cubic megaparsec per year. That's just silly numbers, but the truth is that's a big range. It's between 10 and 200. And then the other thing is that the thing that's really changed compared to before the first detection is that range used to include 0. So now we're closing it from the low end, right? So.
I think we have one more question.
Do you mean that there are no other physical events which will produce detectable gravitational waves other than binaries? Are you looking for them, for other events?
So are there other things that would produce gravitational waves, and are we looking for them? I can't say more emphatically. Emphatically, yes and yes. So yes, there are other things, including mechanisms that we don't even know about, right? I mean, so the searches that I showed you were binaries, and this was so predicted by Einstein. The Einstein field equations were solved for these cases. We know what the waveform looks like. So for those things, we do searches where we actually generate waveforms and ask if our model waveforms match the data. But that is a very, very narrow search looking for this kind of object. We also do completely model independent searches, which are one example. There are many, but I'll give you one example, is to simply take the data stream and to look for excess power in each frequency band. So for example, if it's a supernova, we don't really expect it to be some well-described, chirp waveform like this, but what we will see is we should see a burst of power that increases over a wide frequency band. So we do these sort of model independent searches as well. And then finally, there's another source that we look for all the time, which are continuous waves. So I told you that pulsars can be in binaries, which is what we can look for with these chirps, but they can also be just a single pulsar sitting in space spinning like mad. Now, it turns out that unlike black holes, pulsars are made of matter that has material properties and they can deform. So the spinning pulsar turns a little oblate, or can even have crustal deformations where you can have little mountains on the pulsar surface. And those will be radiators of gravitational radiation. So we look for, and those should be at a very steady frequency. You can just think of it as a little mountain on the pulsar, and every time it crosses your line of sight, it sends out a periodic gravitational wave. So we look for those, and those we use more or less kind of lock-in methods, right? So you're just looking for a well-defined frequency, maybe with some modulation. So all of those searches are going on. You just don't hear about them because those are not the ones that have yielded these first detections.
Okay, maybe one last question.
Well, since you just mentioned this model-independent searches, do you see these events, black hole mergers, also in the independent events?
Yes. If they're, so let me be clear. If they are, have high enough SNR. So interestingly, the very first event that was seen, and so GW150914, it was seen by the model-independent search within seconds after it registered in the detector. Whereas for the waveform matching ones, those are computationally a bit more expensive, so it was seen a little bit later. So the first alerts that we got that this was interesting came from those model-independent searches. But in the end, to get the parameters and to estimate what is it, what are the masses, the distances, etc., that you really do much, much better, of course, with the model-dependent analysis. So, but
Thanks.
good. Right, thank you, everyone.
So let's thank the speaker again. And our next speaker is Mübin Ramazanoğlu from Koç University.